Hello, everyone. My name is Lois Meira from the University of California, Irvine. And today I'm going to present how we demonstrated that it is possible to create mechanical resonance in our Coriolis vibratory gyroscopes using optical forces, and the benefits that can have for the performance. So a gyroscope is a sensor that measures rotation. To do so, it uses elements sensitive to rotation, such as a resonator. Here we can see typical vibration pattern of a resonator. And this vibration pattern, if we apply a rotation around this perpendicular axis, we would expect it, without thinking too much of it, to stay aligned with the frame of the resonator. But what happens in reality is because of Coriolis forces, this vibration pattern lags behind, just like this. This is known as precession, and it's directly proportional to the rotation that the device suffered. So we can use this to measure rotations. This is known as a whole-angle Coriolis vibratory gyroscope, and this is its output. Here in green, we have an scaling factor multiplied by the angular rate, and everything else to the left is, or to the right is, or error in the measurement, or drift. And that drift is proportional to the imperfections in a resonator, such as mismatch in frequency or in quality factor. So on top of having to do this resonator really symmetric to minimize these imperfections, you can see this drift is also inversely proportional to quality factor and to quality factor squared. So having a high quality factor makes this whole error term be close to zero. It can mitigate the imperfections. And that means we have less drift. And drift is what gives us uncertainty when trying to use this gyroscope for inertial navigation. It can mark the difference between navigating seconds or minutes or hours without GPS. So having a really high quality factor is really important. And one of the best gyroscopes in the world is the hemispherical resonator gyroscope, or HRG. HRGs achieve quality factors in the order of several million thanks to three key characteristics. First, they are made with a really high purity, low loss material, fused quartz. And second, they are precisely machined, and they are done one by one and tuned by one by one. These last two characteristics mean that they are limited in cost and size. That's why in our laboratory at UCI, we have been working on developing micro HRG using microfabrication compatible techniques. The process that we use is called microscale glassblowing. It's batch fabrication compatible, and it starts with few silica wafers to which we etch cavities. And then we bond them together, sealing air inside of these cavities. We take this wafer stack and we put it inside of a high temperature furnace where the glass melts and the air expands, creating this three-dimensional geometry. After that, we do some mechanical grinding and polishing to remove extra material, and we release our mechanical resonator, which looks just like this. We call it the dual shell resonator because it's made up by two shells. First one is the inner shell. It's the thinner vibrating element. It's the element sensitive to rotations. And then we also have the outer shell. It's a protective enclosure that surrounds the more thinner and fragile inner shell and protects it from the environment. And it also makes handling easier during fabrication. But to achieve this vibration pattern, traditional HRGs coat the glass with metal to make it conductive and be able to use capacitive forces using electrodes to drive the resonance and to sense the resonance. But this approach is not ideal. This metallic coating introduces additional losses in the glass, thermal losses and surface losses. So in larger HRGs, retention rates are around 60%. That means if you have an original quality factor of 10 million, after coating, it will be somewhere around 6 million. But this is even worse for micro HRG. As you make these structures smaller, surface to volume ratio increases, and surface losses have a bigger contribution to quality factor. That's why retention rates are lower, around 20%, and this is what can mark the difference between navigating seconds or minutes without access to GPS. So we want to get rid of this metal layer completely. That's why our vision is using optical medium instead of capacitive to sense and actuate these resonators. So here in the top, we will have our mechanical structure, the dual shell, with no metallic coating. And then on the bottom, we would bond a photonic integrated circuit, which contains all of the necessary elements for actuating and sensing the resonator. And in today's presentation, I'm going to focus on the actuation part, whether if it's even possible to use light to create the mechanical resonance of this structure. in order to demonstrate this, we built an experimental setup, benchtop setup, where our resonator is sitting inside of a vacuum chamber below millitorr pressure to remove any air damping. And then we have a pre-optic setup outside of the chamber with a mirror focusing the actuation laser beam on the rim of the resonator. For detection, we have a laser Doppler vibrometer, and then we connected both using a Zurich locking amplifier to match the phase of the resonance and measure the displacements. So the point of this experiment, the objective was to generate the resonance by applying a periodic force on the rim of the resonator at the frequency of the natural frequency of 15 kilohertz. And here you can also see a picture of how it looks like under an infrared viewer, this actuation beam hitting on the rim of the resonator. So let's take a look at the results. Here we have laser power, actuation power on the x-axis, and displacement on the y-axis. So it's working. We have a pretty linear relationship between power and displacement, and we're able to measure up to 3 nanometers at 120 milliwatts power, which might not seem like a lot, but it's actually 2 orders of magnitude higher than the noise floor of the optical detection that we are planning to use, which is around 10 picometers. So this is great news. The method is working, but we wanted to know how much we can push this type of actuation, how much displacement we can get, and what are the driving mechanisms for this actuation. So in order to do so, we created models around this actuation, and the first mechanism that can drive this resonance is radiation pressure forces. This is photons impacting in the glass resonator and transferring their momentum. There's a analytical formula that describes these forces. It's proportional to the laser power and 2 main parameters. Reflectivity, so imparted photons that impact and reflect back impart 2x of the momentum, and absorption, which means photons that get absorbed impart 1x of the momentum. The other mechanism that can drive the resonance is thermal forces. So as photons get absorbed, the temperature hits locally, and because of the coupling between mechanical and thermal domains, there's a periodic compression and expansion of the material, which can drive the resonance. To model this, we developed a COMSOL numerical model, and here you can see an example simulation where on the x-axis we have time and on the y-axis we have temperature. And what we can see is that there is both a DC effect, so a local increase in the temperature, as well as an AC effect of the laser power being modulated at the actuation frequency, which changes the temperature in an alternating way, and this is what can drive the resonance as well. So let's compare this to our experimental results. These are the results I was showing earlier, which are for a non-metalized resonator. And if we superimpose the radiation pressure forces, we saw that they match extremely well. And here are the thermal forces. So what is happening here, we have thermal forces computed for different levels of absorption, 1%, 0.1%, 0.01%. The glass that we're using is extremely transparent at the wavelength of actuation that we're using, 980 nanometers, which means the absorption is very small and difficult to calculate. Based on these results, it's less than 0.01%, and both radiation pressure forces and thermal forces are coexisting. But definitely, thermal forces have a minimal contribution, and this is reflected in the resonance frequency of the resonator. Here we have measured it against the incident actuation power, and you can see that it stays within half a hertz of its original value, independent of the power, meaning that the resonator is not heating. So the thermal forces are not dominating. But what if we could affect this absorption and observe how different absorption affects the contribution of the forces? In order to do so, we tested a metallized resonator. And I was just talking about how it's really important that we do not metallize it. We just did this because it's the most accessible way to observe how different absorption values affect this driving mechanism. So if we compare now the experimental measurements for this resonator, the metallized one, to the predicted thermal forces, we see that they match extremely well with the theoretical absorption value of the metal-coated resonator. In comparison, radiation pressure forces now have much less magnitude. It doesn't mean that they are gone, just that they are not dominating compared to thermal forces. And this is again reflected in the frequency and the evolution of the frequency with respect to the actuation power. As we increase the power, resonance frequency shifted by 60 Hertz, meaning that the resonator is heating up as a result of these thermal forces. And last thing is that we measured up to 700 nanometers now at 120 milliwatts power. This is 2 orders of magnitude higher than for the case of the non-metalized resonator, which is a really big bump in displacement, but it comes at a cost, which is quality factor. So for the metalized resonator, quality factor after coating was 270K. And one additional effect that we encountered is that with increasing actuation power, this quality factor degraded even farther below 200K. But in comparison, the non-metalized resonator was able to keep its 1.5 original quality factor, 1.5 million. And we repeated this experiment for different power levels where for each we measured quality factor, and it always stayed within the same value, very close to 1.5 million. So this is exactly what we set out to do with this work, to preserve quality factor in the resonator, and it is really satisfying to know that it's working as expected. So let me just recap the most exciting findings of our study. First one is that we demonstrated that it is possible to actuate these glass structures using only optical forces. We investigated and created models for the two contributions of the optical forces, the thermal forces and the radiation pressure forces. And we were able to preserve the original quality factor of the glass resonators independent of the laser power and without the need of a metallic coating. I would like to thank NCMS for funding this research, and thank you all for your attention. I'll be happy to answer any questions.